Hi, here's a song for you. Some. What a horrible note! I'm gonna try this again. Somewhere over the rainbow, way up high. That's a nice old tune from The Wizard of Oz, and it's memorable for its melody that many people think are beautiful. Now, pretend I'm standing on the chair when I tell you my rash. Whenever you enjoy doing something or experiencing something, the more you understand the elements of that thing, the better you'll get at doing it or experiencing it. The most memorable aspect of music, if music is the thing you like to do, the most memorable aspect of music, many people think, is melody. And so we want to learn how melodies are made and why some melodies sound good and some melodies don't sound good, and how we can learn to talk about them. That means we're getting smarter. Let's see. A melody is a series of pitches put into, we hope, a pleasing pattern. Now, all a pitch is a vibration. A fast vibration makes a pitch that sounds to our ears higher, and a slower vibration makes a pitch that sounds to our ears lower. Now, what makes certain combinations of pitches sound good? And how can we understand the universal mystery of melodies? I say a universal mystery because everybody on earth feels similarly about what melodies are pleasing to us because of the math of melody vibrations. Say I pluck this string. The guy who figured this out first, we believe, is the Greek mathematician Pythagoras. And he took a string like this. You probably wondered what I was fooling with there. Is he took a string and he plucked it. And if it was a string that wasn't just like this, it would make a sound that we would hear. He plucked the string and he listened to the sound it made. Let's say it makes this sound. Ba. Then, being the mathematician he was, he divided the string exactly in half and he plucked it again. Ba! He realized the amount of vibrations was exactly double when he plucked the string in half. And he realized that made a certain phenomenon. The note sounded just like the other note, just twice as fast. And so he felt like it was almost the same pitch. In fact, now we call that an octave higher, and we think of that as the same note, like at the beginning of Over the Rainbow. Somewhere. Sounds like the same pitch. It's not the same pitch, but it sounds like the same note, kinda, doesn't it? And so then, let's say the string vibrates at 440 hertz per second. That means how many times the string vibrates per second. You can see it vibrating back and forth. Dividing it in half, Pythagoras figured out that means it's vibrating at 880 per second. Now the thing is, inside our ears, we have a membrane that's kind of like a string. And you know, whenever we hear any sound, it's because the objects that's vibrating in the first place hits the air molecules next to it, and the air molecules start vibrating at the same frequency, the same speed per second. And each air molecule bumps up next to another air molecule, and they all start vibrating at that same speed until they get to the air molecules that are right in your ear, and those air molecules vibrate up against this membrane in your ear, and that membrane starts vibrating at the same frequency, and so we hear that sound. Now the membrane in our ear is a lot like the string of Pythagoras. It vibrates at the same time that it's vibrating like this. Half of it also starts vibrating on its own. And so naturally, inside our ear, we automatically hear a note when we're hearing a note, and the note an octave above it. So that's why those two notes sound together good to us, because it's what our ear is used to. Now, Pythagoras kept dividing that string, and when he divided the string into thirds instead of halves, he said to himself, this is great because that's a simple ratio. A 1-to-2 ratio is simple, and a 1-to-3 ratio is simple. And that made, let's see, 440 vibrations, 880 vibrations. Now doing a third of a string made how many? Let's see, 1,320 vibrations, which makes ah, ah, da, 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 ah. That's the most pleasing other note to our ears because it's the simplest vibration, which our little string inside our ear naturally vibrates in whenever the whole string is vibrating. So all those notes that Pythagoras discovered by continuing to divide up the string are very far away from each other. Ah, ah, ah. And then the next vibration. Ah. Oh, I can't do it. Ah. But just imagine that much higher. Pythagoras took all those vibrations and put them in the middle of the octave. Ah, ah. And that makes our scale. Ah, 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 ah. Sounds good. It sounds natural to us because all the vibrations that you just heard related to one another with simple mathematical ratios. So you just sing any note, and we call that a scale. It's kind of from the Italian for ladder, and we sing those pitches in a scale in random orders, and that makes our melody. Ah, 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 ah. Any melody that's based on that simple scale we call diatonic. Just what we do. Now if you take a vibration that isn't as simple a ratio relating to any other note, we would call that a little bit more dissonant or chromatic, which is from Greek for colorful. Like this. Ah, 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 ah. Excuse me, gosh, I'm screwing this up. Da, ba, 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 ba. Those notes where I kind of wince on those are the ones that are less pleasing to our ears. The vibration doesn't fit quite as well with the other vibrations. And so you can make your melodies a little bit more interesting, a little more discordant by throwing in one of those chromatic notes. I could do that with Somewhere Over the Rainbow. Somewhere over the rainbow, way up high. Okay, that's one way we can start thinking about our melodies, that they're just scales that are mixed up, what a scale is, why they naturally sound good to our ears, because the relationship of vibrations. Also, now, if you sing a melody that goes up and down the scale without skipping any notes in the scale, we would call that stepwise. Ha, 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 ha. Or smooth, or conjunct, like we talked about last time in class. And a melody that skips lots of notes in a scale, we would call disjunct or a big leap. Ha, ha. So, we've learned about smooth melodies, jumpy melodies, diatonic melodies that sound naturally good because of the way our ears are built, and chromatic melodies which have some kind of shocking notes in there because of the way our ears are built, and that helps us to appreciate what we're hearing when we listen to music. And the next step after that is to think about how melodies are structured. What repeats are there in a melody? What contrasts are there in a melody? We'll talk about that in class and hear more about it next week. Thanks for listening to my video, and now look at my little bullet point presentation, and there'll be YouTube links to click on there so you'll hear melody examples and understand more what I'm talking about. And then just go right down the line in the homework folder and do one thing at a time. There's one video coming up by a woman who describes what I talk about in more detail, and you'll find that very fun and interesting. Thanks. See you in a little bit.